since I really don't know your guys' background, I know a little bit, but not much, and it's varied, and it's happened the same when you're teaching. I'm based on a lot of my classes at BU. I should start. My name is Merav Ofer. I'm a professor at Boston University, and what I'm basing this class is my experience with students at BU that is also very varied. So some shock, some come knowing MHD equations, knowing fluid equations, some not. So please ask me questions. This is all to say, interrupt me all the time. I don't care, okay? Asking questions or even just thoughts that you want to discuss with me, it's very informal. And we should start. So I am slot to give you guys 2 talks, one in shocks and then in particle acceleration, and they are connected. So I wanted to start this one asking you guys a question, and I'm going to answer in the next slide, but wanting you guys to tell me what you think, why we care, why we have even this class, shocks. Anybody wants to ponder about it? Acceleration of solar wind? Well, there is a fact that the sun has a wind and it's accelerated, but it's not directly connected with shocks. There is indirectly, but there is some more direct. Why do we care about shocks? And look, my background is in, my background is on astronomy, and I moved to space physics. And it's very important in astronomy as well. So you can ask this question very broadly. Why do you care studying shocks in astronomy and in space physics? You wanted to say something? Velocity are high. Okay, so velocities tend to be high near shocks. So you're touching a point that shocks do disturb the medium. So if you have a shock, you have a change in the environment. What else? So shocks, there are a type of shocks called bow shocks, and you're right on that, that are our first signature that there is an object coming, okay? So one of the things I'm going to show you, when you have, for example, a planet, and you have the solar wind coming and impinging upon the planet, the solar wind is coming supersonic, great, no idea that there is a planet coming, suddenly is getting information that the planet is nearby, and it needs to slow down to go around it. And the way that this happens, I like to think about shock as waterfall. It's in a very small region of space. You're dividing the medium from supersonic to subsonic. There is a clash, okay? And then the wind starts slowing down around that object. So this is one of the shocks. One of the shocks is bow shock, but there is a much more fundamental answer. Why do we care about shocks? So shocks are universal characteristics. They are present from shocks in the low corona. And when I talk low corona, is the solar wind or the environment near the sun from the surface of the sun to, let's say, 2 solar radii, 3 solar radii, really close to the sun, okay? But you can, if you're studying astronomy or you're going to go to astronomy, you can think about low corona around stars as well, not just the sun. So they are present in shocks in low coronas, near the stars, near the sun, to coronal mass ejections. We're going to see a little bit what is that. And this is a picture of a coronal mass ejection coming out of the sun. This is a magnetized object that is expelled by the sun. So coronal mass ejections travel, and there is a shock ahead of them, usually. Not always, but usually. You have shocks in the low corona. You have shocks in front of planets called planetary bow shocks. You also have shock way, way, way past the planets, 100 times our distance to the sun. So it's 100 AUs called, oops, why this is, there's something, hold on. Let me just check that it's not following any time. Just be sure. Good. And now, how do I go? Slideshow. Okay, I'm good. Where was I? Okay, so this is a picture of shocks in the low corona, okay? And this is an image, not a picture, is an image of 2 subsequent times. This is from Kamen Kozarev paper that detected shocks. And so this is subtracting 2 subsequent images to get in a dashed line. It's so hard to say. We're going to come back to that, why it's so hard to see. A location of a shock, super hard to see. The medium is very rarefied in the low corona, near the sun. So we are going to come back to that. Why do we care to study shocks near the sun? Okay? So this is a paper he showed. And there is also this shock here coming when the solar wind, this is my, one of my fields that I study. The solar wind form a bubble around the sun called the heliosphere. And as we travel through the interstellar medium, this bubble formed this comet shape called the heliosphere. And we need to be deflected, or the interstellar wind deflect around the heliosphere. The collisions, you can think about collisions of 2 winds. So our supersonic wind, a very fast wind from the sun, needs to go through a shock. Same idea as you go in front of a planet. And this shock is called termination shock. So this just to show that shocks are present everywhere in space physics and also in astrophysics. I'm giving you some examples. This is a bow shock in front of a star, Epsilon Eridani. And this is a Hubble Space Telescope images, okay? And usually the winds around those stars are so rarefied, you cannot see their winds. It's very hard to detect, but you can see bow shocks. And one of the things we're going to see, shocks are increase in density. So it's easy to see, okay? So here, this is picked in this artist rendition. This is maybe a bow shock in front of our own bubble, the heliosphere. Again, it will be easier to see if you would be like an alien looking back to our heliosphere because it's denser here, okay? All right, so, yes, please. Is what? Say it again? Mm-hmm. This, I don't remember how this was done. This was, oh, okay, so this is a CME, coronal mass ejection, that was ejected from an active region. And you can see here in dotted line where the coronal mass ejection is there, starting to propagate. And it's forming a shock that is this dashed line. And this is a subtraction between 2 images. So you see this in other stars, the shocks, but you also see them in galactic bubbles, in galactic centers. Near the galactic center, near active galactic nuclei, they eject matter called galactic bubbles. I have a colleague at BU that studied them, and it's very interesting. It's related with how the evolution of chemistry in the galaxy happened. And they are gigantic structures traveling the galaxy, forming a shock. So those are scales from parsecs. So now we are talking about solar radii forming shocks near the sun to parsecs. So shocks are present everywhere in completely different scales, okay? And what is universal about them, and we think, this is what will be interesting in this class for you guys, that you're going to study, at least what I'm going to try to show you, is the basic stuff I would like you guys to get out about the physics of shocks. And you can, in practice, apply it to solar radii to parsecs, to very disparate sizes. The other universal characteristics of shocks are they accelerate particles. They're a very good location for accelerating of particles. So this is why you can guess why I'm giving the second class after this one, particle acceleration. Because we are going to use a lot of the concepts that you guys are going to see this morning for the afternoon session, okay? And here, for example, the CME that come out from the sun, and this is in white light here. And the CME comes out, you see the structure, and it's accelerating particles, and they all run into the detector. So you see all this, it's not just dirt in your detector that you need to clean your lens. Those are particles that are, it's a snow shower that hit the detector coming from the CME, okay? Okay, so outline of the class. This is kind of a crash course, what I think you will need to know about shocks, or kind of the basic stuff that is useful, your key tool, what you should carry with you about shocks. So what we're going to see is what is a shock, how a shock forms, really briefly. And then we're going to go through this couple of equations, I hope you don't fall asleep on this part, that are called the Rankine Hugoniot jump conditions. And you can derive those equations from the MHD equations that I think Amitava went through yesterday, okay? So I'm just going to show you one derivation so you know how to do that if you want. But I'm basically going to present the equations and play with them a little bit. Because I'm going to play, I would like to get this shock adiabatic equation. This is one equation that you can get out of this Rankine Hugoniot conditions. And then we're going to go through overview. Which type of shocks exist? Parallel, perpendicular, weak, strong, a little bit of a flavor. You guys get a feeling about the type of shocks, and then we're going to finish with examples, okay? All right. So, again, I'm going to hammer the same point. Shocks are universal. So this is a cartoon that we produced for the book. Last time I taught this class here. That, sorry, they show a little bit out of focus. But you can see here the idea why we did that was to show that here is a CME, a coronal mass ejection coming out of the sun, and it has a flux rope here. And the solar wind coming out from the sun is going around this flux rope. And it's the same idea as a solar wind going around a planet. It has to slow down. There's an obstacle. And again, you come from this notion, okay? Why, okay, let me ask you in a form of a question. Why does the solar wind have to go around the flux rope, the CME? Frozen influx. Can you phrase it in a different way? Right. So two ionized plasmas don't mix with each other unless something happens. Anybody knows which process can allow them to intermix? Reconnection, right. So in these cartoons, I'm talking about processes that are related with ideal plasma, right? It's a process when we are not allowing the plasma to reconnect, to connect to each other. They're deflecting with respect. Now, there is this process reconnection, which could be a total different class, that you allow these plasmas to talk, to intermix, okay? So the solar wind is magnetized, is ionized, so it has to go around this magnetic flux. It cannot just enter, right? So it has to go around, it's going fast, so it's going to form, we are going to see under certain conditions, a shock ahead of the CME, okay? So you will have supersonic environment and a subsonic environment here, okay? Now, we talked about the heliosphere, and I work on these both fields, and I like to think they're very similar. because here we have the sun with a very fast wind, supersonic, has a magnetic field. You have a hard time seeing here, but has a magnetic field. The interstellar medium is another ionized fluid. It's not totally ionized, but it's basically ionized. And it has a magnetic field. We don't really know where it's pointing, but we have guesses. And this environment, this ionized plasma, has to go around the heliosphere. Why again? Because there are two ionized plasmas, right? And we're not including reconnection here, or loads of reconnection when the two can totally intermix, right? So it's going around. So if it's fast, faster than the ambient speed, it's going to form a shock, bow shock. Same thing with the solar wind. So the solar wind is going to do termination shock, okay? Very similar to the CME case. And now finally planets. Planets don't have winds. So it's similar to maybe the CME flux orb. Flux orb doesn't have a wind in itself. So the planet has its own magnetic field here. This is Earth case. And the solar wind is impinging on Earth, and it's going through a shock. Okay? Okay, so what is a shock and how a shock forms? So I took the liberty to scan a lot of my notes, so you're going to see a lot of handwriting. Hope you understand my handwriting. Maybe it will make it cozier with this handwriting. So it's related to a process. We're not going to go through this whole detail of that, of what we call a nonlinear stiffening, okay, of waves. Why shock forms? Think about, so here I'm going to give you guys an example related with sound waves, okay? But you know, you probably saw it already. I'm just going to repeat again. Magnetized medium or ionized medium have waves. They produce waves. You can think about waves as the intrinsic characteristics of the plasma, okay? If you don't have a magnetic field, sound waves, right? You shake a medium, you can have a sound wave. You can have Langmuir waves. If there is a magnetic field, you have Alphen waves, okay? So plasma has certain waves, and they're happy to travel in the medium. Under certain conditions, they start piling up. So here is me trying to draw a wave, okay, the full line. And as time passes, even small amplitude waves can stiffen and start distorting. The crest won't be that round anymore and start becoming steeper. So another way of seeing that is if you have the wave, this is, imagine that is not like that really, but a sinus. The back can start becoming much more quadratic here. So a way to think about it, I like this example, it's a propagation of a sound wave, okay? So the speed, the sound wave speed can be derived by this. The pressure here, P is pressure and rho is a density, okay? So you need to know how pressure varies in the medium. So let's take the example that we are in what we call adiabatic medium, okay? Adiabatic medium has this kind of a behavior, okay? P over rho gamma. Gamma is a adiabatic index, okay? So you take the derivative of that, you find out that the sound speed in an adiabatic medium is not constant, has to do with pressure, and has this index alpha that depend on the adiabatic index, gamma. So it really will create a problem for the sound waves. If you have a medium where this happens, the back of the wave is going to move faster than the front of the wave, and it's going to make this wave stiffen and form a shock. It's inevitable. So what will happen is that this wave will become nonlinear and will stiffen into a shock. So what will happen is you will have an intrinsic wave in the medium that form in a very small region of space a shock. So there are other microphysical processes that can delay that, can make the wave broader, for example. We are not going to go through that. The whole physics, how really a shock form. We are going to say that if you have a shock, it's going to be, we know that from nature, in a very, very finite, narrow region. And what is kind of amazing, it does work. We basically are going to say that the microphysics of that shock won't affect the medium, what we call upstream, the shock, and the microphysical of the shock won't affect downstream. This is not strictly true, but we are going to show that the Rankine Hugoniot conditions work. And the Rankine Hugoniot conditions assume that the medium ahead can be treated as an ideal MHD form. And the medium downstream the shock also can be an ideal MHD, okay? Inside the shock, there is a breakdown of the ideal MHD equations that we are not going to enter into details. And this will be interesting. We are going to derive from the ideal MHD equations this set of relations called Rankine Hugoniot that describe what happened with a medium when it's going through a shock from upstream to downstream. And the only thing that will matter will be the shock strength, quantities like that can be shock strength, the angle between the normal of the shock and the magnetic field, quantities that can be derived from ideal MHD equations that don't depend on the microphysics. And it does work. It's a way for you to kind of say, okay, there is a physics much more complicated that I can shove under the carpet, treat an ideal MHD before and after this catastrophe happened, the shock, and still I will be able to describe the medium, what happened after the shock, and we will show in the afternoon, I will be able also to describe acceleration of particles without entering all the microphysics in the shock, okay? Okay, so the Rankine Hugoniot relations will be such that they will conserve mass, magnetic flux, and energy. So what are those relations? Yes, please. Mm-hmm. Okay, so here, depend on which reference frame you are. Okay, so it really will depend on the steepening. So we are going to derive the Rankine Hugoniot conditions that will boil down to the speed of the shock. And the speed of the shock will be related with the strength of the shock. You can't tell, I cannot tell you, no. I need to assume something, strength of the shock. Let's come back to that question when I derive the shock adiabatic equation. But purely in that, I cannot tell you. It depends on the process of the steepening. How strong is the steepening? I couldn't hear you. Well, it will be a disturbance moving faster than the sound speed. So in that, the sound speed limits the lower speed of the shock. So we will derive them. If it will be just sound speed, this thing is just propagating like a wave. And I will derive for you the speeds of the shock. And you can see how the speeds vary depending on the shock strength. Okay? All right. Oops, yes. No, it depends on processes that stiffen. In this case of a sound wave propagating in an adiabatic medium, it will stiffen. Depending on this, which equation of state, which medium you're going. But in an adiabatic, yes. Okay, so Rankine Hugoniot relations. One of the MHD equations I think you saw yesterday was a conservation of mass. You're all familiar with this equation, right? So it's just described, this is where the density and how it's varying in time and in space convected with a plasma, okay? It's here. And what we are going to derive in the next slide, that you're going to be able to derive this relationship. Let me go for next slide and then come back to this. I think it's easier. So here's a conservation of mass that tells you how the density evolves in time and in space. And I'm only going to do it for this equation, so you guys get the feeling how these Rankine Hugoniot are derived. But we are not going to do it for the other equations. You can take a little, you know, this kind of pill boxes, little volume, and it has an area A2 and an area A1, and this has a certain normal n, okay? And you integrate this equation in a volume. So you integrate in a volume, this is 0. You integrate in volume, is also 0. And you can separate them in, so you have this term here, volume, the other volume. And this surface, this volumetric, can be converted to a surface integral. And now you do the usual trick to set the volume 1, in this volume V1, V2, going to 0. So this term goes away. And you're also going to say that the area A1 and A2 are the same, A, okay? So you get this type of a relationship, okay? And A1 and A2, now it's A prime. So you get this. Oh, sorry. Oops, let me go back. You get this one term, this term, and now A1 and A2 are A prime, and you got rid of these equations. And you have here a dot product, so you need to take into account the normal to the area. So this is where the normal comes. This will be the normal of the shock, okay? Normal to the surface. So you get that this term is equal to that term, and let me just go back. Why you get the equal? Because one normal is pointing that way, and the other normal point this way. And because they're equal, the inside of this integral should be equal. And what you basically end up deriving, that the mass flow in of that surface, the shock, needs to be the same mass flowing out, okay? So this is this relationship typed, not with my handwriting. You have the mass flow in to the area of that volume has to be equal to the mass flowing out. So just to give you again in perspective, if the ideal MHD equations are valid, upstream the shock and downstream the shock, you can derive automatically this, right? Again, it is interesting. I always like this dialogue between two different fields. You have whatever microphysics in the shock and a total different area, fluid description. And you're saying that no matter what's happening, whatever chatter is happening here, noisy people screaming, whatever, if the fluid is valid out both sides, I can derive that the mass flow going through the shock would be conserved. Okay? So it's interesting. independent of the physics of the shock, I can derive that the quantities upstream the shock, rho 1, U1, are equal to rho 2, U2, okay? And then I can write them in these squiggly brackets. Squiggly brackets will be what I'm going to use for Rankine Hugoniot and making this expression much simpler like this, okay? So you just know that I'm saying this quantity is conserved. Okay, so this is the first Rankine Hugoniot relation. And what is, just to emphasize again, it's mean if you're giving me the conditions downstream, rho 1, U1, I will tell you the conditions downstream, rho 2, U2, together, the multiplication. Okay, now you go to the momentum equation. I'm not writing, I'm just writing this way quickly in a conservative form. And you go the same thing, you integrate in a volume around the shock, you do all the math tricks, and you end up with this relationship. Now, what is these brackets? Are the Rankine Hugoniot nomenclature that mean that this quantity upstream should be equal to the same quantity downstream, okay? It's complicated. There is a magnetic field, there is a thermal pressure, there is speed, but at least I know that this is conserved, okay? So the shock. You go through this monster of conservation of energy equation, and you get that this quantity is conserved, okay? That is the energy flow. So you can write it like this, okay? So this is for the density, momentum, and energy. And now you want to take also the fact that you don't have a magnetic monopole, and you derive it in a volume, and you're going to get that B1 times the normal is equal to B2, the normal. So now I'm having a relationship between the magnetic field upstream and downstream. And now you're taking the electric field that is related with Maxwell equation from del B del T. You integrate on the volume, you get this relationship, E cross N. So the tangential meaning, and now I'm taking that E that is not in the direction of the normal, but tangential is conserved. Well, okay? So you need to, and if you have the electric field, you know an ideal MHD is V cross B. You can write down this relationship like that, okay? So you need to write, so those are basically the Rankine Hugoniot relations. And you need to figure out a coordinate system. There are different coordinate systems. I'm not going to cover here. There's a de Hoffmann-Teller coordinate system. There is a coordinate system moving with a shock. You have to pick a coordinate system, whatever you want. Now I'm just going to show you a coordinate system when you are taking the normal to the shock and the tangential component relative to the shock, to the surface. And this is how the Rankine Hugoniot look like. We're not going to manipulate them much. I just want you guys to be familiar how they look like. So you have the conservation of mass that we saw, and those will be broken down as UN, U along the normal to the shock, okay? And now you have, from the momentum equation, this relationship is conserved, and you're going to break down in this equation and this equation. That makes the tangential B with a normal U, and you have U, the tangential U and the normal U. You have these two equations. And now the conservations, from the conservation of energy flow, you get these equations. And now the other one from the B dot N, you get Bn conserved. And from the electric field, that is U cross B, you get these equations, okay? So this is what you have. And basically, they tell you the story of how the ideal MHD flow talk to each other, how the medium before the shock and after the shock are related. They're related by these equations, okay? And they're called the Rankine Hugoniot conditions. Okay, so you can go through classifications. This Rankine Hugoniot can describe not just shock. They can also describe just discontinuities. I didn't assume anything when I did this whole derivation. I just said there is something there that separates two ideal fluids. It has a normal. This can also be a discontinuity, like we are going to see if I get to it. I don't know by the time. I doubt we're going to get it. Heliopause, when they're not shocks, just discontinuities, okay? This could be another class if I don't get to it. What they call tangential discontinuities. It's like the last wall outside of the heliosphere is a tangential discontinuity, okay? But they can also describe shocks. So this little table, I think I stole it from Amitava's book, I'm not sure. I don't remember my sources anymore, maybe. That has this classification is if you don't have a jump in density between upstream and downstream, those are just rotational discontinuity. If you do have a jump between them, you can have a contact discontinuity. This is a heliopause, for example. We are going to go the rest of today's to study shocks. Shocks are when you have a jump in density before and after, and you also have a jump in speed, okay? So we're going to get to shocks. If there's a miracle, I might get to discontinuities. But if not, you know that those Rankine Hugoniot describe discontinuities as well. Okay, if you just go through the math, you will see there is a problem. If you go to the equations, you see there are 12 equations. The 4 upstream parameters are specified. You say, okay, I have a medium that have a density, a speed, a magnetic field. And I want to know what's happening downstream. And you realize you need another variable. So here come for your question, speed of the shock. So I can get the speed of the shock here, related to how the medium is moving. But I need another unknown. So one of them will be that I will specify, I have 7 equations for 8 unknowns. I need another on my pocket, and what I need is the strength of the shock. I call delta here. I need to know what is delta. I need to specify that. Rho 2 over rho 1. What is this jump in density, okay? So here are lots of quantities that I think Dana went with you guys yesterday, but I'm just going to emphasize again. You have quantities in plasma. We are not going to use it much the rest of the class, but just I'm showing here called alpha and Mach number that has to do with the speed over the alpha and the background alpha and speed. You also have sonic Mach number, speed over the sound speed. But one thing we are going to use will be this quantity delta. That is the angle between B and the shock normal. This will be important, okay? Okay, now I'm going to jump 20 pages of just boring algebra. It's not 20 pages, I don't know. A couple of pages of boring algebra. When you go back to the Rankine Hugoniot conditions and do some massage, you're massaging the equations, throwing one into the other, more algebra. A couple of hours later, you can get to one single equation. You can massage them to one single equation called shock adiabatic equation. It's very useful because basically you don't have to memorize all this or don't even have to know all these Rankine Hugoniot conditions. I don't memorize this one, but it tells you that the shocks can be described by one single equation. So this is equal to 0. So this is the quantities upstream, okay? UN1. This is in that reference frame of normal and tangential, okay? So this is the upstream normal speed. This is the upstream alpha in speed. You should know that if you're the medium that you are. And you are going to relate this equation to delta. Okay? So if you want to know the speed that the shock is moving, you need to specify delta. If you specify delta, I can give you what is the speed of the shock. But you will have to specify too what is theta 1. What is the angle of B doing with the normal? Okay? This is where we're going to see enter if the shock is perpendicular, parallel. It will depend on this angle. What the upstream B is doing with the normal. Okay? And once you know UN1, based on delta, you can derive the rest. You know, rho 2, based on rho 2, rho 1, you specify by delta, you can derive all the other quantities. Okay, so let's go another couple of minutes and then have a stop, a break, okay? Let's start with overview. This goes until 10, right? So, yeah, so let's do another 5-7 minutes and take a break. Start in type of shocks, okay? Parallel, perpendicular, weak, strong shocks. So weak shock is when you're saying this is a very weak shock. Delta, the jump between rho 2 and rho 1, is almost 1. There's almost no change in density. Very weak shock. Just for you guys to know, the shock, the termination shock, turns out to be around between 2 and 3, the strength of the shock. When the spacecraft Voyager crossed it, the strength of the shock was kind of not super strong either, 2. Okay, strong limit will be this delta M that we're going to show for an adiabatic medium is 4, the maximum strength of a shock. For a non-adiabatic medium, if gamma is not 5/3, you can have stronger than 4. But usually medium are adiabatic, so the maximum strength of a shock that people have, the intuition, you talk to people, what is the maximum strength? They're thinking 4. In fact, I'm going to make this point later, that near the sun, when the medium is not adiabatic, you can have stronger shocks. But in general, an adiabatic medium is 4. And then parallel shock is when that theta 1, I lost the 1 index here, between B and N can be 0, perpendicular when they are perpendicular. And we also call quasi-parallel or quasi-perpendicular. And quasi-perpendicular is when this angle is larger than 45 degrees. Okay? Yes? So when it's gamma, it's 5/3. Okay? 5/3, right. So it's CP over CV 5/3. Okay, so I'm just going to show you 2 of these nightmare slides. And why I decided to show that, because I want you guys to get familiar. If you've never seen these equations, you have to get familiar with going to the shock adiabatic equation, taking this limit, what you're going to get, okay? So let's go back to that equation and take a limit of a weak shock, okay? A weak shock delta is 1. So let's substitute 1, 1, and 1. Everywhere when it's delta, there is 1, okay? So let's just do this limit and then take a break. Delta is 1. I go back and I put 1, 1, 1, 1, 1. And what I get, I simplify my shock adiabatic equation to this one, okay? You can do it home if you're bored. Just do the algebra. And the solution of that are 3 solutions, okay? Turns out that the speed of the shock the normal speed 1, can be the alpha in speed 1 cosinus of theta 1. I didn't specify if the shock is parallel or perpendicular, or I let theta 1 be whatever. So I get this. I also get that I can have two solutions when the speed of the shock can be the sum of the alpha speed and the sound speed minus this monster. Or you can have the alpha plus sound plus this same monster. And if you're familiar with MHD waves, those is a slow magnetosonic speed, fast magnetosonic, and here is the alpha speed with an angle here, okay, theta 1. And what is interesting, these waves have very different characteristics. I'm not going to go through characteristics of waves, but you can see that here it's mixing magnetic field and compression sounds. So it tells you that in the weak shock limit, the shocks are going to move with 3 different types of speeds. So if you're an observer, you're out there seeing a very weak shock, somebody tells you, I saw a very, very weak shock, delta 1. You are waiting for a speed of that shock to be very slow, or intermediate speed, or fast, okay? And let me just see what the name, okay. And yeah, this is a fast, slow, and the theta 1 is what we talk. So let's take a break for 5 minutes, and then we come back. voice. Hello, hello. Good? Yeah. Okay, so let's start again. One thing that I realized talking to some people, for me it sounds really loud, the sound. Is it good for you guys or too loud? Too loud. Okay, so I will be deaf with my own voice. That I realized when discussing with some people, I wanted just to clarify a couple of points that I think will make it a little bit more intuitive. When we talked about, this was one of the questions, adiabatic medium or isothermal medium, for example. When we're talking about compression of shocks, okay? And I said that the maximum compression is 4. We're going to show in an adiabatic medium, okay? A way to think about the distinction, so really gamma is Cp over Cv, but the way to think about it is input of energy in the system. So if you have a adiabatic, it's like the solar wind expanding. Whenever you're putting in the system, it's coming out. This is a adiabatic medium. If you're constantly heating the medium, is isothermal. Isothermal, you're keeping the temperature. If the solar wind expands, the temperature wants to fall. In medium that expand, temperature wants to cool down. If you're saying, no, I'm going to keep the solar wind isothermal, the temperature will be constant. This requires input of energy, constant input of energy with radii, okay? Near the sun, people think that gamma is close to 1.1. It's not 5/3. There is some input of energy, okay? This is one clarification. Another clarification that somebody was asking me, are all shocks ahead of the CMEs faster than the environment speed, faster than the Alfvén speed, actually the question was. And it's not. You can see here in the weak shock limit, okay? So for weak shocks, the speeds of the shock can be very slow, can be as slow as a slow magnetosonic speed, okay? Slow magnetosonic speed can be super slow, can be slower than the Alfvén speed, okay? And one of the misconceptions, I'm going to repeat that later in the class, strong shocks in an adiabatic medium, and strong, when we say strong, we're going to talk about 4. Thinking about adiabatic medium, we are not going to have all these solutions. We are going to have fast magnetosonic speed. So the disturbance will need to go faster than the magnetosonic speed. Why people care so much about strong shocks is because what you're going to see in the afternoon. Particle acceleration is related with the strength of the shock. One of the beauties that you can derive a power law coming from the strength of a shock. So if you give me the strength of the shock, I can describe the type of shocks here, but I will be able also to describe a power law of particles. And people are after the Holy Grail to describe how particles are accelerated. So they are looking into strong shocks, okay? So just wanted to clarify these 2 points. Okay, so we saw weak shock limits. Let's go and decide we don't care about strength of shocks for now. Let's just go parallel shocks, parallel and perpendicular shocks. So if you go parallel shocks, this means that the magnetic field is parallel to the normal, okay? And you go back to the shock adiabatic equation and you substitute theta 1, 0. And you keep everything else. Delta you keep because I didn't specify. And you get this one, okay? So you get 2 solutions. Parallel shocks can have 2 solutions. Can be like that or like this, okay? And again, Alfvén, this is the Alfvén speed, and S is the sound speed, okay? So if I go here and I said, okay, let me take delta 1, I get for a parallel weak shock, the solutions are that the shock is going to be a sound wave or an Alfvén wave, basically. Okay, so as delta increases, now let's go back to here and say, let me look at the solution not when it's a weak shock, but I'm going to increase delta. See what happened when I go to I'm still in parallel shocks, but I'm going just to increase delta. So if I increase delta, I get that UN1 increases. Stronger shocks, stronger speeds. Stronger disturbance will give you stronger shocks, okay? And you get to these quantities, this maximum value that is to do with gamma. You can just set this constant. Gamma plus 1, gamma minus 1. If you substitute gamma is adiabatic 5/3, this is 4. 5/3 plus 1, 5/3 minus 1, you get 4. Okay? If gamma is 1.1, this is not 4. Okay? Anyway, you take the limit when delta increases to this value, UN start going really fast to infinity. It's a very fast shock. Okay? So, delta M is a maximum shock strength. And like I said, for 5/3 is 4. This is where I think the concept that you have strong shocks, delta is 4. But it's gamma 5/3 to give you that. And you get, this is, I just mentioned, when gamma is 1.1, the compression can be larger than 4. Okay, so I'm just going to play with this quantity, delta M minus delta. Delta M is just this quantity. I define gamma plus 1 over gamma minus 1. And I can write it like this. And then I go back to the expression, still just for parallel shocks, okay? UN1 can be written like this, delta M over minus delta. You can see that when the compression gets maximum delta M, this thing shoots to infinity, okay? And you can see that as delta goes to delta M, UN1 goes, this becomes smaller and the speed goes faster, okay? All right, this is parallel shocks. Perpendicular shocks. Now I'm going not to specify delta, but I just want, okay, I have comments, maybe too many comments. So if you go to perpendicular shocks, this, okay, my comment here. This type of shocks parallel are important in reconnection. Outside the scope of this lecture, but they appear in reconnection. Okay, perpendicular shocks. You specify delta 1 pi over 2. You say this is a field that is perpendicular to the normal of the shock, okay? And is just another comment. It's not just that it's mathematically interesting, pi over 2, 0. We are going to see for acceleration of particles, they accelerate very differently if the shocks are parallel or perpendicular. They are not just related with the shock strength. There's other factors coming in. And the fact if the shock is parallel or perpendicular will be crucial for the acceleration of particles. So this is why we're going through this zoo of shocks, okay? So you have pi over 2 perpendicular. You go back to your shock adiabatic equation, and you get one solution only, okay? This monster here. This is your monster that you get. It didn't specify what delta is. For a weak shock, it's a fast magnetosonic speed, okay? Now, for a strong shock, when delta starts going to this maximum value, the same way as parallel shock, the speed of the shock shoot up. So for a perpendicular shock, same thing. You have a strong shock. Stronger shocks are related with fast-moving stuff. Okay. So this is parallel perpendicular in general. Let's take the other limit that people love, strong shocks. They love that because they are the good accelerator of particles, because delta is big. So I'm going to go back to the shock adiabatic equation and take the limit when delta goes to this maximum value. Now I'm not going to specify if theta is parallel or perpendicular. Just going to let it be whatever. So the question you can ask yourself, which type of shocks exist in nature that are strong? This is what you're asking. So I go to the shock adiabatic equation, and I take this limit, of strong. And how I do that, I can neglect terms in this limit, delta m over delta. And what you get after a lot of math is that you're getting fast magnetosonic, but below that, the slow intermediate doesn't exist. You get solutions that don't propagate. So what you get is, I'm going to show in a minute, the summary of the shock solution, that the adiabatic equation have 3 roots, slow, intermediate, and fast. The weak limit, you're going to get the usual. Alpha in waves, slow magnetosonic, and fast magnetosonic. And as the shock strength will increase, the speed of the slow and intermediate shocks merge an intermediate value, shock strength. And as the shock strength increases beyond this value, I'm only going to get one solution, fast shocks. So here's a cartoon that shows you what I am talking here. This is delta, the strength of the shock, and the speed of the shock. They're related. So now the exact form in this will depend on alpha speed and sound speed, which one is larger than the other. But the gist of it, that as you go to stronger shocks, you have faster speeds, fast moving stuff. When you go to really strong shocks, 4, you're only going to get a fast moving shock, fast in the magnetosonic speed. And what the takeaway message from all that is that you can have solutions. You can have shocks moving slow in nature, slower than the magnetosonic speed. They will just be weak. They exist, but they will just be weak. Okay? So for acceleration of particles, less interesting. But they exist. Okay? All right. So now I'm going to just make a couple of just comments and give you examples. Okay? Yes? So the magnetosonic speed was right, thanks for the question. It's right at the beginning, would have been good right at the beginning, because then I would have slowed down. Magnetosonic speed is this one. Is the alpha speed squared plus the sound speed squared. The magnetosonic squared is the sum of the alpha plus, okay? Yeah, so the fast magnetosonic has all this term as well, okay? But this, yeah, and because depend on this angle theta 1, okay? Okay, so this is the end of lots of equations, so you can relax. Here are a couple of comments, okay? One, thickness of shocks. We didn't talk at all about thickness and physics of shocks. So I just wanted you guys to get just a flavor of what people are studying in terms of characteristics of shocks, okay? Thickness of shocks will depend on microphysics. It will also depend on this angle. This is theta 1. It also will depend on what we talked about, the Mach number. Mach number was the speed of the shock related with the local alpha speed. So there is lots of quantities that will dominate the thickness of the shock, but in general, a perpendicular shock is usually thin. Parallel shock are much thicker. If you're a spacecraft going through shocks, if the shock is parallel, you will see much more microphysics than perpendicular. Perpendicular, you blink, you're on the other side, okay? I didn't talk at all here, and I won't have time, on lots of waves and interesting stuff that happen near shocks. And they're related with the microphysics of the shock that I'm not discussing here, But just to give you a flavor, that those waves and particles accelerated in the shock can interact with waves and can make this picture that we draw based on ideal MHD not exactly correct. They disturb the medium. It's not just a quiet fluid upstream and downstream. There's noise. So there is oscillations here. This is before a shock. The waves and noise. If you go to the Iowa website, I can send you guys the link. There is a radio group there by Don Gournett that has lots of these waves converted to sounds. So it's really neat to listen. And it's one of the ways when you understand the microphysics of shocks, if you have a satellite, you know a shock is coming because you're going to hear those singing along waves just before you cross, okay? Just again, to give you a little bit of the flavor of science, I joined the Voyager team just before we crossed the termination shock. And the discussion in the team was how we are going to know if the termination shock is coming. We need to listen to the shock. So you go back to this class and you open your book and you're trying, what are the characteristics of shocks that will allow me to predict that the shock is coming? Again, if it's a perpendicular shock, what turns out the termination shock was a perpendicular shock, it's going to be a blip. You better be listening. But some of the radio folks in the team said, let's listen to waves ahead. Waves do escape the shock and start telling us that we're coming, that there is a shock coming. So this is a Jupiter bow shock. It's 6 kilohertz, it's a radio station. I like to imagine you have a radio station in kilohertz, nothing comes, silence, and then bzzzt, you have like a noise that comes when you're just before a bow shock. And just before we came to termination shock, there was bzzzt, a noise there. And after the shock, there is more waves. The medium is not exactly quiet, okay? So this is an interesting stuff that happened. We're not going to discuss it. There's lots of turbulence and lots of interesting kinetic physics that happen around shocks, okay? Okay, so I wanted to give you some examples. Yes. Yes, please. Previous. No, no. Again, there is a microphysics that will enter, but no. In this case, it's a fast. It's a strong fast. Again, it really will depend. It will depend also on the strength of the shock. Yes, this is overall yes. There are, yeah, but you need to really enter in the microphysics to give you the thickness. No, 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 but it's to give you kind of a feeling what happened in the thickness, okay? You have a stiffening of a wave. Think about the wave trying to stiffen. There are what we call losses in the plasma that try to make the wave not stiffen, try to broaden it. So it's a fight between the process of stiffening versus dissipating and broadening that will determine that thickness. But let me just to add something else. All this physics is going to happen in a kinetic scales. And what we say, it's a jargon, kinetic scales. It's mean on scales where particles motion is important. And the particle motion is much, much, much smaller than the fluid scales. So even though you might have a very broad shock, it's on the scale of gyroradii. It's scales of how particles are moving. Still fluid is okay if you go to larger scales. Okay? Okay, so observations. I have 8 minutes to give you a couple of slides of observations, okay? Here is an Earth bow shock, and this is, I found fascinating in space physics, that aspect. You go and you study this class I gave you, lots of dry equations, but you have the description of shocks. And then you look at data, and it's nothing like you expect. It's more or less, it's some interesting, but I wanted to give an example of some stuff that look like what you expect, but some that doesn't. And this, I think, would make exciting. You realize that that simple description is not really valid. So, for example, Earth bow shock. One of the things a shock does is to take something very fast and slow it down. So you have a very fast wind speed, and it's going in this thickness. This is the thickness of the shock, okay? So look how interesting. You have a satellite that has cadence minutes. We are measuring it. We can really go through a shock. What astronomers, this is what excited me when I moved astronomy to space physics. Space physics, you can go through a shock. Astronomy, you're just looking at the shock. But space physics, you can send a satellite and go through a shock. So you are upstream, you're going through shock, and downstream. And you see what Rankine Hugoniot predict. You have a fast speed is going to become slow, and what a density is going to be compressed. So you take a low density to a very compressed region. So this is a typical, what you expect in a shock, fast to slow, rarefied to denser, okay? But you have all these oscillations here that is not fluid-like. Some stuff in the shock got, at least for a couple of minutes ahead of the shock, disturbing the medium, okay? Termination shock, same thing. You had a perpendicular shock, and you have solar wind before the speed, supersonic, and this is, they have this funny 243, day 243, so days. So in a couple of hours here, you went to supersonic to a subsonic, and the magnetic field went for a low value to a higher value. So shock compress and increase magnetic field. But you have, but it's not just a jump. Rankine Hugoniot just said jump. It's not just a jump. You have all this microstructure. That is some microphysics, okay? But here is an example where the books doesn't work really well. Here is 2 examples of why it didn't work. Let me skip to this one. This is the data from the termination shock that show a fast-moving plasma went through what I like to call the waterfall, dropped to a slow speed. We went from 380 kilometers per second to 100 kilometers per second, okay? Slower speed in a very narrow region of time, in hours. It's a perpendicular shock, very thin waterfall. And the density should increase. This is black, the red dots. It did increase. It was not a very strong shock, 2.7. You can go to your Rankine Hugoniot conditions and plug for perpendicular shock what you expect to happen in terms of temperature. So you have speed before, after, density before, after. You say it's a quasi-perpendicular shock. You know the magnetic field, and you predict what the temperature is. This comes from the energy equation, the thermal pressure. And you have a prediction that it's going to go to this black line. And it doesn't. It's go to the red line. Much colder. So this was a big surprise. The shock did not behave as a one fluid ionized matter. Yeah? So this is, again, I thought I had slides about it and I took it out. There are techniques how to determine the normal of the shock. So you basically, you need 2 vectors, right? And you need to cross product to get the normal. And there are different techniques. You would like to have several satellites looking, but you don't. You have one data point going. But there are techniques that determine that normal. So without going into the details, they best determined it's a fit that they make of the rotation of the magnetic field. I can discuss with you later. But they are pretty, it's a very good technique that can give us a normal. Right. The thermal density. So one thing, so there are surprises. I'm not going to go. Why the surprises? Another surprise I'm going to talk in the afternoon, we thought that shocks, and this is what I'm going to try to sell you in the afternoon, shocks are good particle accelerators. Here's a termination shock that is not super weak. It's not delta 1. It's not 4. It's 2.7. It's intermediate. We should have expected a certain acceleration of particles. And here's a snapshot of particles. This is intensity in energy, and you have different populations. We're going to talk some of that in the afternoon. Before and after. This is kind of a snapshot in days. Before the diet, after the diet. And you can see that we expected, based on what I'm going to show in the afternoon, a behavior like the dash line. That this red will be accelerated and jump to the dash line. That this one are going to jump here in terms of the intensity will increase in energy. And before and after look the same on this energy and beyond. Some of the low energy were accelerated, but some were not accelerated. So there were surprises. The shock was not a good accelerator, okay? Another example I want to give you is shocks driven by CMEs. And so we are sitting, this is nice because we are sitting on Earth. We have continually monitoring. It's different than in termination shock. We have one data point Voyager going through. We are sitting on Earth and continuously seeing CMEs hitting us. So although it is far away from the sun, it's 200 solar radii away, the shock evolved a lot. But we do see CMEs and shocks passing by. So here's an example of a CME where when you have a flux rope coming by, you'll have this kind of a signature in magnetic field. This is magnetic field. It's a little bit hard to see. You can see in the speed is so low here that it's jump. There is a shock. It's really hard to see here. There is a shock that come ahead of the CME, and then the CME come. So you're sitting here. You first will see the shock, and then the CME. Okay? I am done with my time, so I'm just going to flash a couple of slides that I wanted you guys to see. What will be important in space physics, and here is an example of here is magnetic field jumping ahead of the CME, and then you see the CME. It's a shock. What will be important in space physics is to know when we are seeing a CME and a shock coming by, where are we sitting in reference to this shock? Are we at the nose of the shock or on the sides? And one of the things that, do I have a slide of that later? No. One of the things that is important is if you are here, for example, this is a parallel shock. I have a slide, I think, later on. Let me see if I can find it really quick. Actually, I think I put it on the afternoon session. The shocks can be parallel or perpendicular, depending where you are in the CME and how low in the corona you are. So bottom line, we would like to understand how shocks originate near the sun and how they evolve towards us. So we would like, so even in a CME, there are continually accelerating particles. We would like to know where they're accelerating. Where, with location on the CME, and how low in the corona they are. So let's see if I can, more stuff I wanted to show you guys. This is an interesting slide. I just wanted to get a flavor. All this mass I showed you, it's nice, but you would like to detect shocks, and it's really hard to detect shocks because they're so rarefied. So there are a couple of papers here. Like, look at this. This is from John Raymond. I took. They only have 5 cases of shock detected that they can really say this is a shock. And here is the compression ratio, 1.8, 2.2, weak shocks. Some of the open questions, it's my flavor of open questions in the field, are how low in the corona shocks form? And maybe you can ask yourself how, if you're talking about strong shocks, delta 4, how low in the corona? Because you see lots of particles that have energies, very energetic, GeV. So here's an example of the low in the corona. Here's a CME. You see a CME in the sky propagating, and you detect energetic particles, GeV, on the ground that are so energetic, came to Earth. You know they're related, but you really don't know where they were generated. GeV are so energetic that you probably need a strong shock. So the question, where in the low corona they form, and how the shock evolved. And this is just to end, are the instabilities. There's lots of interesting physics in shocks. You see, this is a white light, you see lots of instabilities. And this is an MHD simulation. It's really hard in MHD to really describe those instabilities. Are those instabilities important for particle acceleration, for example? Okay? So hope you enjoyed this class. And I'm going to give it to Lika. Thanks.